I'm the manager of Steelmaking, Casting and Refractories Group here in East Chicago. The group is part of Process Research Division, one of the 3 divisions in East Chicago Center of R&D. We are responsible for developing innovative technologies and process solutions that enable the plants to produce steel faster, at lower cost, and with the highest possible quality. Process research is very well equipped with a lot of laboratory capabilities. We have advanced analytical lab, and we also have pilot scale facilities and a lot of simulation capabilities. All of that enable us to provide really scientific-based, well-rounded, data-driven answers to all the technical problems that we face, that our plants face.
Sinter plant is actually a key preparation facilities for blast furnace iron making. We prepare the iron bearing raw materials for stable and efficient blast furnace operations. And also we have online off-gas analyzer and electric preheaters. With all these new features, we're able to help Sinter plant in addressing the challenges in raw materials. For example, with more and more fines and recycled materials in the raw mix, we're able to help Sinter plant to improve their process and also addressing more challenging environmental requirements.
We are equipped with a 100-pound vacuum induction furnace, which allows us to achieve a precise chemistry control down to parts per million. Every steel product we design here starts development journey from the vacuum furnace. This vacuum furnace is equipped with a precisely tightly sealed alloying addition system and sampling system and the temperature control system. So one of the focus in our group is the cleanliness investigation. We need to control our chemistry very precisely, and we may try many different chemistries. That's why we need a vacuum furnace. This vacuum furnace is very important.
In all steel, there is some residual particles that we want to remove. And the last chance of removing those particles before the steel solidifies is in the caster mold. So what we want to do here is we want to maximize the time that the steel flows to the meniscus of the mold so that any trapped argon bubbles or inclusions can float to the surface and be removed. If they aren't removed, then they will eventually solidify into the steel shell and cause a defect in our final product. Obviously, you can make models in various scales. Depending on what type of things you want to study, you then select the scale for that study. The one-to-one model that we have here is one of the few actually in the world, because many people opt out for a 1/3 scale model. In a 1/3 scale model, you can only duplicate what they call Froude number. In a full scale model, we can duplicate Froude and Reynolds number. And that may not mean much to the layman, but to the scientific world, it means you get a little bit more closer to the real thing.
This is our ASCAT testing laboratory. ASCAT is our automated steel cleanliness analysis tool. When we want to test steel cleanliness, we'll start with a sample of steel and we'll mount it in clear epoxy. And then a technician will polish this to a mirror finish so that we can look at the cleanliness inside the steel. We'll mount 6 of these samples in a carousel like this. And then this carousel goes into the ASCAT instrument, and each sample is tested sequentially for cleanliness. We've got an energy dispersive X-ray with EDX inside, and that's going to measure every inclusion in the steel. It's going to measure the size, the shape, the number of inclusions, and it's going to give us the chemistry of every single inclusion in each of the samples.
This is we call a confocal scanning laser microscope. In steel processing, we have to heat up the steel to very high temperatures. And at higher temperatures, it's very difficult to identify different phases because the human eye cannot see the glowing of the infrared. So with this equipment, we can use laser to identify different phases at very high temperature up to melting point of liquid steel of 1600 degree centigrade. And it's only one in the United States for steel industry.
This is our Cathodoluminescence microscope. What happens is that we have an electron gun that produces excited electrons, excite the compounds and minerals, and it glows, and here's what you see. I'm looking for defects, impurities, and inclusions. Different colors means different compounds. Green, for example, here is like spinel that we find in the steel. So when we find green in steel, we know right away it's an impurity, it's bad for steel. And we can easily identify them through phase identification by the use of excited electrons.
Basically, the Gleeble is a fully integrated computer control system. We can do tension, we have torsion system. You actually can pull, when you're heating it, you stop the heating, you pull and twist at the same time. That type of testing goes on for line pipe. We can do hot ductility testing. We can do strip annealing, flat tensils. There's a lot of functionality with this machine.
So by modifying the chemistry of the mold powders and the slags, we need a tool to show us if we are really achieving that compositions that we are looking for. And one of these techniques is the hot stage microscope, which is also known as HSM. We mainly use this technique for mold powders and mold fluxes. It's important to know the melting behavior and softening behavior of these fluxes, because these fluxes are going to go in between of the steel and the mold during continuous casting. And it's very important for us to know how it behaves.
The purpose of this furnace is going to measure the softening melting point of the iron ore to determine if this iron ore is acceptable or not, to have the high fuel efficiency, to have the good so-called stability, and also to have good productivity. So this is a very important furnace, so-called softening melting furnace. So far, probably it's a unique, only one in our group. ArcelorMittal group is the only one here.
For this lab, I normally focus on the failure analysis in the refractory, and then characterization and qualification process. This is a specific equipment measuring the high temperature mechanical strength. So the concept is that steel making is a high temperature process, so we just evaluate the different material at an elevated temperature. Understanding the refractory material is very, very essential to have a success in the steel making process and continually reducing the cost and optimize the process.
Here we have a flashbed welding process. It's a laboratory scale pilot unit, which we can use it for developing welding process offline using different weld product, different AHSS grade, new Gen 3 products, and so forth. We can develop process parameters offline. We can also use this equipment for knowledge building of the welding process. We have recently adapted a global flashbed welding project for development of welding process parameter studies and understanding for knowledge building in European plants.
I work with the high performance computing and data analytics lab here. We call it smart manufacturing now, where we use high performance computing and data analytics, various tools available for those smart manufacturing. So we are very fast in adopting those tools as a company so that we can actually stay ahead of the competition. So this gives us a competitive edge, and we believe the companies, those who are adopting this kind of technologies faster, they will be actually changing the game of this industry. So it's really a game changer for us. So we have software vendors, startup companies, we have university partners, so it's pretty exciting, so you're all ready for the future.
The most important thing for us is to remain competitive in the industry. Cost reduction is a critical component of that. Also, developing new products that meet the demands of the market today is very essential for us to survive. And therefore, process research provides all the support needed in order to develop the processes and the techniques that enable us to achieve those goals.